All right, let's talk first law of thermodynamics. First, we got to make sure we get our terms correct. So we have, what is this, 2, 4, 6, 7 important terms that you have to make sure that you understand. The first is the idea of a system. Remember, a system is just a collection of stuff. Usually for us in thermodynamics, at least in AP Physics 2, that system will be gas trapped usually in a cylinder of some kind. The environment is just everything outside of that. Okay, internal energy we already talked about in a previous video. That is just the sum of all the internal potential and kinetic energies of all the atoms rocketing around inside the object. Now, since this is a gas that we're usually talking about, there will be no potential energy. It will just be kinetic energy of the molecules bouncing around. Remember that the temperature measures the average kinetic energy of all the molecules in the system, and we measure that in Kelvin. Heat, we talked about in our last video. Remember, heat is the transfer of this internal energy from object to object. Remember that this heat transfer continues until we have thermal equilibrium, and that occurs whenever the temperature of the two objects in thermal contact become the same. And our last one is work. So work comes to us from mechanics from last year. So remember that work is a force that causes a displacement. That's in units of joules. Conservation of energy. So let's go back to mechanics. Remember, conservation of energy is just the energy we start with, energy 1, right over here, plus any work that's done will give us what the energy will be at the end. Remember, if there's no work done, then the energy at the beginning equals energy at the end. But in the bigger sense, conservation of energy means that we start with a certain amount of energy, stuff, and then we either add to it or subtract from it, and we end up with a new pile of stuff, this energy. If I subtract energy 1 to the other side, then you can see that work equals how much the energy of the system will change. So for thermodynamics, we're just expanding conservation of energy. So the first law of thermodynamics, all it does is two things. It just adds a new way to add energy to the system. So our new way to add energy is direct transfer of heat into or out of the system. So like if you take a candle and set it under a balloon, you're adding heat to the balloon, and the balloon will expand. And we're also including, instead of just the mechanical energy, kinetic, gravitational potential, spring potential. We're going to add U. And U is the internal energy of the system, or the gas in our case. This equation becomes pretty long and cumbersome with all these different energies involved in it. So what we do when we're beginning physics is we eliminate things, just like in mechanics, we neglected air resistance and friction at the beginning. So we're doing the same thing here. We're going to neglect all the mechanical energy and just be left with internal energy. So what we end up with is that the internal energy of the system changes depending on whether you add or subtract heat from the system, or whether the system does work or you do work on the system. And that's it. So don't make it hard. This is just conservation of energy. We need to make sure we get our sign conventions correct. This first one's really simple. Q is positive when heat is added to, absorbed, or input into the system. Okay, so like if we take you and set you out in the sun, heat's going to enter your system, and you will warm up, and your internal energy gets higher. Conversely, if it's a cold day outside and we take you and set you out on the sidewalk, then heat will leave your body, and heat will be removed or withdrawn, or you're going to expel heat, and so your internal energy will go down. So that's negative. Now, a little bit harder is the ideas of work. So if work is done on the system by the environment, then, in this case, a gas, the energy of the system goes up. So the gas will be compressed. So if we have a balloon and we do work on the balloon by compressing it, we're doing work from the outside environment, pushing into the system, causing the energy of the system to increase. That's why we have a positive sign here, because the energy of the gas will go up in the balloon as we compress it. Okay. On the other hand, if the system does work on the environment, say, like, for instance, say you lift something. When you lift something, you're transferring energy from you into that object, and therefore energy transfers from you to it, and your internal energy goes down because you're doing work on it. Same thing is true for the gas. If a gas expands, When it expands into the environment, it's moving the environment, and therefore it's losing its own internal energy. So that's negative work because its internal energy will go down. Let's take a blowtorch and we're going to hold it to a cylinder filled with gas. The gas is going to absorb heat from the blowtorch. The gas will expand as it heats up, forcing the piston upward, lifting the piston. Heat's entering, so that's positive heat, Q. The gas is expanding, so therefore it's losing energy, so we'll have negative work. And then what happens to the internal energy of the gas trapped in the cylinder? Well, it depends on which one's bigger. Did we add more heat than energy we lost due to the gas doing work, or vice versa, or are they the same? It's possible that the temperature or internal energy of the gas could stay the same. So don't make it hard. It's just energy and energy idea. So I've said over and over and over again that we're using gases in the first law of thermodynamics. And the reason why is because gases have the ability to expand and contract, meaning they can do work. Because remember, work requires force and movement. Solid and a liquid can't really do that. If we take a desk and we heat it up with a blowtorch, it's going to expand a little, but not enough to really do any sizable work. In thermodynamic machines, like the engine of your car, or like at a nuclear power plant, or a gas-powered power plant, all of these things, the main thing they do is they heat up a gas, adding heat to it, so that it expands. And when it expands, it makes things go. Either makes your car go, or generates electricity. So since we're talking about gases, remember that we have the ideal gas law in play, and we also have learned internal energy of a gas. The average is equal to 3/2 Boltzmann constant times time. Now, if we take this equation and multiply by the total number of atoms in the gas, then we will find the total energy inside the gas. We have this new term, 3/2 N kb delta T, and that will tell us how much our internal energy changes. N, the number of molecules, and Boltzmann's constant. If you multiply those together, those are exactly the same as these terms over here, which is N, the number of moles, small n, and R, capital R, the ideal gas constant. So this half of the ideal gas law times 3/2 will tell us the total internal energy of the gas. Remember, work done by the gas is a little bit different here. So since we are using FR cosine theta, first of all, it's easier to figure out forces using pressure in a gas, and that pressure is always perpendicular to the surface, like we learned in our gas video. And if we take that pressure and multiply by the change in volume, that's our movement, then we will get the work done by the gas. There's our negative sign, because if the gas does work and expands, so if we have a positive volume change, then we'll have negative work because the energy of the gas will decrease. So let's put it all together. PV diagrams. Let's talk about the temperature first. What temperature is this point right here? Well, we have the equation PV equals nRT. We know R is a constant, so we got that one. We can read pressure and volume from the graph. So if we go across here, we can read the pressure. If we go down here, we can read the volume. So we have PVR. If they give us the number of moles, then we can calculate the temperature of this point. Let's say we start at this point right here, and we can go along each of these different directions, A through H. Now, which path would you take to move to a higher temperature? Remember, PV equals nRT. If I want a higher temperature, that's proportional to P times V. So I need a higher PV value. So I just need to go up in pressure, A, up in volume, C, or both, B. Any one of these, A, B, C, will take me to a higher temperature. Conversely, a lower temperature, well, if we have to move down in pressure or volume or both, so E, F, and G will take us to a lower temperature. H and D, we have conflicting things. We're going up in pressure for H, but down in volume. So it depends on the relative magnitude of each and whether we would go up or down in temperature. All right, let's see if you can rank these temperatures on these points right here. So point A, B, C, and D. How would you rank those temperature-wise? Well, if we take a look at it, remember the PV value tells us our temperature. So the higher the PV value, the higher the temperature. So this is 5P times 3V, so that's 15 PV. B would be 16 PV, so B is a little warmer. C is 15 PV, so C and A are the same temperature, and D is by far the coldest. It's only, what is that, 12 PV, so it's coldest. A and C have the same temperature, so they're along something what we call a isothermal line. These isothermal lines are lines of constant temperature. So everywhere along one of these lines, we have the same temperature. These lines will be hyperbolas or inverse graphs because if we're keeping nRT constant, then P is proportional to 1 over V, which gives us an inverse graph. The further you move from the origin down here, the higher PV value you have and the higher temperature the isotherm will be. All right, now let's talk about work. All right, if we move to the right on a PV diagram, the gas will be expanding, and since our equation right here is negative P times delta V, and pressure is always positive or 0 at the lowest, then whenever volume change is positive, we're going to have negative work. So this is negative work from here to here. Now, we could easily just multiply this pressure times this change in volume. But if you notice, that's the same as finding the area of this area underneath the graph, this green area. Rank the work done from greatest to least in these three processes. So we can do this two ways. We can say, well, they all have the same change in volume. So A has the highest pressure, so there must be the most magnitude of work for A, and then B and C. Or you could look at it from an area standpoint. We have a small area under C, we have a bigger area under B, and the largest area under A. When we move to the left, what's the work going to be now? Well, when we move to the left, we're going to have a negative change in volume, but our equation is negative P delta V, so we end up with positive work whenever we move to the left. So all of these, any kind of movement to the left is positive work. So can you calculate how much work each one of these processes does in terms of P and V? D to D prime has a change in volume from V to 4V. So that's a volume change of 3V. And the pressure is 3P, so we would have 9 PV. And if we do the rest of these, we'll see that this one, it has an area of 4 PV, and this has an area of just PV. And they're all positive, shows it to the left. Okay, what about moving up and down vertically? If we do that, notice there's no PV value, there's no change in volume. So therefore, no matter what the pressure is, it doesn't matter, there's no work done because there's no volume change. A gas can travel two different pathways from point I to J. First question is, will the temperature change of the gases be positive or negative? So if you go along path 1, is that a positive or negative temperature change? Well, we're going up in P and V, so that's got to be a positive temperature change. And 2 must be a positive temperature change. All right, question number 2. Along which path will the temperature of the gas change the most? Well, it's going to be the same, right? We have the same temperature here, I, and the same temperature here, J. So however you get from I to J, whether you go some crazy route, it doesn't matter. You have the same exact beginning and final temperature, so the change in temperature will be identical. Will the work along the path be positive or negative? Well, they're moving to the right. That's a positive change in volume, which means negative work. So both of these will be negative work. Question number 4. Along which path will the work have the greatest magnitude? All right. So unlike temperature change, work depends on the area under the graph or the pressure for our change in volume. Notice that from moving from I to J, we have the exact same pressure change. The exact same volume change. All right. However, path 1 has a higher average pressure than path 2. So therefore, there will be more magnitude of work done along path 1 than along path 2. Or you could say the area underneath path 2 is smaller than the area underneath path 1. So we have a larger magnitude of work for path 1. We can calculate heat because we know now how to calculate work, and we know how to calculate the change in energy. The change in energy is from 3/2 nR delta T, and we can find the temperature change on our PV diagram. We can find work by finding the pressure and change in volume, or the area, on our PV diagram. So finding work and change in an internal energy by finding change in temperature on our PV diagram, we can work backwards to find the heat. Okay? Now, you may remember from chemistry there was an equation called Q equals mc delta T. And there's an equivalent one for gases. It's the heat equals nc delta T, where n is the number of moles. We could use that as well, but that is not part of our curriculum on the AP Physics 2 exam, so we'll just find it by using the first law of thermo. In each of the processes that are shown in the figure, indicate whether the value is plus, minus, or 0. So is the temperature change for path A, is it plus, minus, or 0? Is the internal energy change plus, minus, or 0? Is the work plus, minus, or 0? Is the heat plus, minus, or 0? Pause the video and see if you can work these out quick. So let's take a look at a couple of these. Look at path A. So we start here and we move up and to the right. So we're moving up in temperature. We can also see that we're moving to higher isotherms. So the temperature must be positive. Temperature change must be positive. And since temperature change is related to the change in internal energy, there should be a delta T right here. That's a typo. Then these two always move together. They're not the same number. This is in Kelvin and this is in joules. All right, we've moved to the right, so that's negative work. All right, but now what's Q going to be? Well, delta U equals Q plus W. So that means Q must be bigger than work, positive-wise, so that we have some positive delta U left over. Okay, you can work those same arguments for each one of these all the way through. Notice that the work is 0 for process C because we're moving up and down. So the heat and the delta U will be the same value in joules. And then along path B, we start and end on the same isotherm. So therefore, there's no change in temperature. So therefore, there's no delta U, change in internal energy. And so therefore, these two numbers are the same, but one is positive and one is negative because of the way they are in the equation. Let's talk cycles. A cycle is when we begin at one point on a PV diagram and we end up back at the same point. So like in cycle number 1, we go A, B, C, D, back to A. Cycle 2, we go A, B, C, back to A. Now usually on our test, they will give us something that will have some straight lines on it and not be all curvy like this, cycle 3, because that would require sometimes some calculus to figure out the area under the graph. So if they're going to require you to find the area, to find work, then it will usually be some sort of straight line. During a cycle, you can figure out each individual process and then add them all up, like to find the work between A and B, and the work between B and C, and then C and D back to A, and add it all up. Or the same thing for the change in temperature for each one. But if you notice for the cycle as a whole, we end up back where we began. So we're back at the same temperature we started. So therefore, there is no internal energy change for a complete cycle when we end up back where we began. That means that delta U drops out of the equation, and we end up with Q equals negative W. Another thing to remember about a cycle is that we can use the area to figure out the work. So in this particular cycle, A to B has negative work, negative 10 PV from this one, because we have 2 times 5 here. And then we have 0 work for the vertical. And then from C to D, we have positive work. So that's 3 times 5, so we get 15 total. If we add all that up, we end up with 5 PV, positive. That's the same as the area inside, because this bottom part here cancels out. The positive 15 from top to bottom and the negative 10 from AB down will cancel out this bottom part. So we end up with only the area inside. And that's the way it always works for a cycle, no matter what the shape. So anytime we have a clockwise cycle, In a clockwise cycle, we'll have negative work because in a clockwise cycle, we'll have more negative work done up top than we have positive work done below. And that means that our heat will be positive. In this kind of cycle that goes clockwise, then heat is put into the system and the system does work on the environment. That's called a heat engine. That's like the engine inside your car. That's like at a power plant, like a nuclear power plant, producing electricity. Now, if we go the opposite way, like this one, this is a counterclockwise cycle. In this one, we have more positive work from C to D than we have negative work from A to B. So therefore, we have a net positive work done. That means that work is done on the system. Remember, the system is being compressed. And heat is being expelled from the system, okay? So work is done on the system in order to expel heat from the system. This is a refrigeration cycle. So this is exactly what happens in your air conditioner or in your refrigerator or freezer in your house. They run a counterclockwise cycle on a PV diagram. We have 4 special processes that we need to make sure that we know the names of so that when they come up on the test, we know what they're talking about. One of them we've already talked about. Number 3 down here is isothermal. That's where the temperature stays the same. It always looks like a hyperbola. It's a curvy line. And so Q equals negative W. If we have a constant pressure process, isobaric, it moves right and left on a PV diagram. So the work is easy to calculate. A constant volume or isochoric or isovolumetric process is one that goes straight up and down. When that happens, there's no work. Therefore, delta U equals Q. Now our last one is one where Q is 0, where there's no heat transfer. This is usually a very fast process or a well-insulated process, so that no heat can transfer in or out of the system. And so therefore, delta U equals the work. This is a curved line just like an isotherm. You can tell that it's different, one, because it's steeper, but also if you take the PV values on, say, the ends of that curve, you can see that they're not the same PV value. Whereas on an isotherm, if you take a PV value anywhere along that curve, it'll always equal the same number. So let's see if you get it. So here's our sample question. Label all the processes and fill in the table with pluses or minuses. So I've labeled the first one. Number 1 is adiabatic. Okay, this adiabatic is where Q equals 0. And notice it's steeper than our isotherm. How do I know number 2 is an isotherm? Well, this is 5P times 2V. That's 10 PV. And then down here, this is 1P times 10V. So that's also 10 PV. So this has the same temperature end to end. So it's an isotherm, where number 1 is steeper and won't have the same temperatures on end to end. So therefore, it's an adiabatic process. Number 4 is an isobaric process, and number 3 is an isovolumetric or constant volume process. All right, see if you can fill in the table. Did you get this? These are the answers for this particular arrangement of process. All right, that's it. That's thermal physics for the first law of thermodynamics and PV diagrams. In our next video, I'll have a few examples from thermodynamics that we'll work through. Bye-bye.